Welcome to The Explainer. Today, we're diving into one of the most powerful, yet kind of secret tools in all of science and engineering. This is a method that lets us see the future, test things that are impossible to test, and understand everything from a supersonic jet to the flutter of a tiny fly's wing. It's called dimensional analysis. And to see how it works, we've got to start with a huge engineering problem. So just imagine for a second you're an engineer. You've been given this monumental task. You have to guarantee that a brand new, insanely complex, and mind-bogglingly expensive piece of hardware is going to work perfectly before a single bolt has been tightened. How in the world do you do that? Take this. This is a model of an Arleigh Burke-class destroyer. The real thing is almost 50 times bigger. You can't just build a billion-dollar warship, cross your fingers, and hope it doesn't flip over in a big storm. You have to know. So how do you test it before you build it? Well, the answer is a technique that honestly feels a little bit like magic. It's called dimensional analysis. It's basically a secret language, a set of rules that lets engineers use these small, cheap models to perfectly predict how the massive, full-scale thing is going to behave. And this is the key. It's not about being the same size, it's about achieving the same similarity.
To get how this superpower works, we have to rewind all the way back to a simple rule you probably learned in kindergarten. That's it. That's the whole foundation. You can't add apples and oranges. And in the world of physics and math, that's not just a cute phrase, it's a stone-cold law. You can't take a number that means distance and add it to a number that means time. It's just nonsense.
This rule has a fancy name, the law of dimensional homogeneity. Sounds complicated, right? But all it really means is that for an equation to make any sense in the real world, every single piece that you're adding or subtracting has to be measuring the same kind of thing. Every term has to boil down to the same fundamental dimensions, like mass or length or time. Take a look at this famous beast, the Bernoulli equation. It describes how fluids move. Now, it looks like a mess, but you've got three main parts here. One for the static pressure, one for the pressure from the fluid's speed, and one for the pressure from its height. And here's the cool part. When you break them all down, every single one of those terms has the exact same dimensions, the dimensions of pressure. They're all speaking the same language. So, if every term in an equation has to have the same dimensions, what happens if we use that rule to our advantage? Well, you get something incredibly powerful, these special dimensionless numbers, which engineers call pi groups. Now, there's a whole 6-step recipe for finding these, called the method of repeating variables. We're not going to do the math, don't worry. The key thing to know is that this process can take a super complicated problem with tons of variables, like speed, density, size, you name it, and boil it all down to just a handful of these powerful, dimensionless numbers that tell you everything you need to know. And here are the superstars. These aren't just random numbers. They're powerful ratios that tell a story. The Reynolds number, for example, it compares how much a fluid wants to keep going versus how sticky it is. The Froude number compares that forward motion to the pull of gravity. And the Mach number, that one's famous, it compares an object's speed to the speed of sound. If you find the right magic number for your problem, you've basically found the cheat code.
Okay, so that brings us to the real question. How do we actually use these magic numbers to make a little model in a lab act exactly like a full-sized car on the highway? The secret sauce is a concept called dynamic similarity. And it's an amazing idea. It says that if you can make those key dimensionless numbers, like the Reynolds number, exactly the same for your little model and your huge prototype, then the physics will be identical. The way the air flows, the forces, the drag, all of it will scale up perfectly.
All right, let's put this to the test. Let's say we build a perfect 1/5 scale model of a car to put in a wind tunnel. And what we want to do is simulate the real car cruising down the highway at a steady 50 miles per hour. So here's the million-dollar question. To get that dynamic similarity, to make the air behave in the exact same way for the tiny model as it does for the real car, how fast do we need to crank up that wind tunnel? Now, your gut might say, 50 miles per hour? But you'd be way off. The answer is a staggering 221 miles per hour. That is faster than a high-end race car. It's totally counterintuitive, right?
So why so fast? It's because that magic number, the Reynolds number, depends on both size and speed. Since our model is 5 times smaller, we have to blast the air 5 times faster to get that number to match up. But when it does, the forces we measure on that tiny model tell us exactly what the drag will be on the full-size car. That's the superpower.
But, it's not always that easy. In the car example, we just had to worry about one magic number. What happens when a problem has two competing numbers? This is where engineers really have to get clever.
Let's go back to our warship. For ships, two numbers are super important. The Reynolds number for skin friction and the Froude number for making waves. But here's the catch-22. To match the Reynolds number, you'd have to tow the model impossibly fast. But to match the Froude number, which governs the waves, you have to go really slow. You can't do both at once. So engineers have to choose. For a ship, waves are the biggest deal, so they match the Froude number and then use calculations to correct for the rest.
Okay, but what if we took this whole idea to its most mind-bending, extreme conclusion? What if we wanted to study something tiny and crazy fast, like a fruit fly? It's basically impossible to stick sensors on its wings. So, could we use dimensional analysis to go the other way? To build a giant, slow-motion model?
The answer is an absolutely wild yes. Everybody, meet RoboFly. This thing is 100 times bigger than a fruit fly. It flaps its wings over 1,000 times slower. Oh, and it doesn't fly in air. It flies submerged in 2 tons of mineral oil. So why on earth all these bizarre changes?
It's because every single one of those changes, the massive size, the slow speed, the goopy mineral oil, was all done for one reason. Listen to how the head scientist, Michael Dickinson, put it. They did it all just so they could match the Reynolds number of this giant robot to the Reynolds number of a tiny fruit fly. And because that one magic number matches, the invisible swirls of air and the complex forces on RoboFly's wings are a perfect, scaled-up version of what happens on a real insect. This giant, slow, oil-soaked robot becomes a perfect window into the secrets of flight. It's all possible because of scaling. From designing our cars to understanding how a tiny fly stays in the air, this hidden language of scaling and dimensionless numbers is all around us. It's the engineer's secret superpower. The only question is, now that you know about it, where are you going to see it next?